plugged a new mouse into your computer and it just works? You know, no setup, no installation, just magic? Well, behind that seamless experience, there's this critical, totally invisible piece of software doing all the heavy lifting. So today, let's dive into this hidden world and talk about the unseen engine that lets your hardware and software actually talk to each other, the device driver. I mean, think about it for a second. It's a really simple question, right? But the answer? Whoa, it's incredibly complex. Your mouse is a physical thing, a piece of hardware. It speaks a completely different language than your operating system or your favorite game. So how does that physical click, that little plastic switch, turn into a command in a digital world? That's the exact problem that device drivers were built to solve. They're basically the universal translators of a computing world. Okay, so what is a device driver officially? Well, you can think of it as this specialized little program that lives in the absolute core of the operating system, what we call the kernel. The kernel is like the OS's central nervous system. The driver's job is to be the go-between for the I/O manager, which is the part of the OS directing all the input and output traffic, and the actual physical hardware it's meant to control. So yeah, it's the bridge that connects the physical world to the digital one. Now, you'd probably think it's simple. One device, one driver. But, it's rarely that easy. For most hardware, it's really more of a team effort. A single device is often managed by a whole stack of drivers, and each one has a very specific job to do, all working together in a nice, orderly line. And this stack idea is everywhere. Your graphics card, your storage, even the file system uses this model. When some application needs to do something, the request starts at the top and travels down this stack. It might go through an optional filter driver first, which can tweak the request. Then it hits the main function driver that does the real work. And finally, it gets to the bus driver that talks directly to the physical port, like your USB or PCI slot. So let's break down what each of these players on the team actually does. All right, so here's how that team is set up. Down at the very bottom, you've got the bus driver. This guy is the manager of the physical connection, the USB port itself, for example. Its main job is to notice when new devices are plugged in and tell the system, hey, we've got a new arrival. Now, the star of the show is the function driver. This is the main driver for your device. It knows everything about it, all of its unique features. And then you have the filter drivers. These are optional, but they're super powerful. They can sit above or below that function driver to add new features, like maybe extra security scanning for a USB drive, or to just change how the device behaves. So, if all these drivers are a team, how in the world do they talk to each other? I mean, they're not just shouting commands into the dark. Nope, they use a very specific, very structured language to pass messages up and down that stack. And that language is built around something called an I/O request packet, or an IRP for short. The best way to think of an IRP is like a digital work order. It's a neat little data packet that has everything a driver needs to know to do a job. Read 5 kilobytes from this exact spot, write this chunk of data, or even something like, hey, get ready to go to sleep. Literally every single action gets wrapped up in one of these IRPs. And this is where things get really tricky for developers. Trying to manage all these digital work orders by hand is, frankly, an absolute nightmare. Just look at this list of worries. Should I process this request right now and make the app wait, or do it in the background? What happens if the user just yanks the device out mid-transfer? How do I handle the computer going to sleep or waking up? If you get any of this wrong, you could get data loss, or, even worse, a full system crash. So you can imagine, with all that complexity, things went wrong a lot. This is what led to the infamous blue screen of death for years. And that's exactly why writing drivers directly against the kernel isn't really the standard anymore. To tame all this chaos and make life way easier for developers, Microsoft created a modern solution, the Windows Driver Foundation, or WDF. The whole point of WDF is pretty simple. Hide all that complicated, error-prone stuff. It's built on top of the older, much more complex Windows Driver model, or WDM, and it basically creates this protective layer. It gives developers a clean, modern system that handles most of the routine, boring tasks for them automatically. And that is so important because it lets them focus on what makes their piece of hardware special, not on reinventing the wheel. Now, WDF actually comes in 2 main flavors, and this really shows a core trade-off in how systems are designed. First, you've got the Kernel Mode Driver Framework, or KMDF. This runs deep inside the OS kernel, right at ring 0, for absolute maximum performance. It's essential for stuff like your graphics card. But then you have the User Mode Driver Framework, or UMDF. These drivers run outside the kernel, in the much safer user space. And the trade-off? Well, a UMDF driver is way safer. If it crashes, it usually won't take your entire system down with it, which makes it perfect for peripherals like webcams or USB sticks.
So, when you put this all together, what does using a modern framework like WDF really get you? Well, the advantages are huge, not just for the people writing the drivers, but for all of us actually using the computers. Hey, remember all those headaches we talked about with managing IRPs by hand? Well, WDF basically just solves them. It automatically handles most of the plug-and-play stuff, like when you plug a device in or take it out. It deals with all the incredibly complex logic for power states like sleep and hibernate. It gives developers a clean, simple way to work, and it just massively cuts down on the amount of code they have to write just to get something working.
And that right there is the real payoff for developers. Instead of spending, say, 80% of their time wrestling with the messy plumbing of the operating system, they can spend that time making their hardware faster, adding cool new features, and, just building a better product. The framework handles all the grunt work.
And for us, the people actually using this stuff, the benefit is immediate. Better drivers, built on a solid framework and tested with tools like Driver Verifier, which is basically a stress test for drivers, mean fewer blue screens. It means your computer wakes up from sleep when it's supposed to, it feels responsive, and it's more secure, because a lot of the common problems have already been solved by the framework itself. It's really the foundation of a stable system. So the next time you plug something in and it just works, you'll know about this incredible unseen engine of drivers and frameworks making it all happen behind the scenes. It does make you wonder, though, as we move into a world with even more complex, interconnected devices, IoT gadgets, AI accelerators, the whole shebang, what's the next frontier for this foundational technology? What will the next generation of drivers need to do? Now that is something to think about.
If you want to help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.